Okay guys, welcome back. You can kind of consider this Unit 11, Day 3 notes. We're going to pick up where we left off on Day 2. We talk about some multiplicity, end behavior, roots, and how to sketch these without a calculator. Alright, so let's pick up right here. This particular example, again, if you remember from the previous lesson, what I encourage you all to do is multiply this out so you get the first term and the last term. So in doing that here, I'm going to have a negative x squared times x cubed, which gives me negative x to the fifth. And then I don't really care what's in the middle. My last term is going to be a negative 1 times negative 9 times that negative. So that's going to give me a negative 9. Alright, so now basically we need to do three things. We need to determine what the roots are, we need to determine the end behavior, or tails, and we need to get the y-intercept. And there's no particular order. We want to get that information before we start to sketch. So, okay, let's get my roots. Alright, so I've got x squared minus 9, set that equal to 0. You can see here x is going to be plus or minus 3. I've got x cubed minus 1 equals 0. X cubed equals 1. X equals 1. Now, that one happens to have a multiplicity of 3. Why does it have a multiplicity of 3? Because it's x cubed. Okay? So that means it's going to do something at that particular root. Alright, so let's see. If I take a look at this first term here, I can see that for my tails, or end behavior, I've got a negative odd. So a negative odd is going to look like this. Remember how you can tell it has a general downward flow as you go left to right. And then finally your y-intercept, which again you can always find by just setting x equal to 0. If you do that up in the original equation, what you're going to have is negative 9. Okay, so let's put this information on the graph. I've got plus or minus 3. I've got 1, so those are my three roots, plus or minus 3 and 1. My y-intercept is a negative 9. And I know my tails do this. Now the multiplicity of 3, that particular root right here, means the graph is going to flatten out. It's still going to cross through, but it's going to flatten out when it gets to that. Okay, so I've got something that's going to look kind of like this. I know these can get a little tricky to draw. And then it comes back down and joins that tail. So there's a very quick example. Roots, end behavior, y-intercept. Those three things we're going to do for every problem. All right, I'm going to kind of skip through quickly here. Pick and choose certain ones to do. Multiplicity of 1. Let's take a look at this example here, example 5. All right, so very quickly, my roots. This one's nice. It's already completely factored. So basically x equals negative 1, positive 3, negative 4. Right? You just take the opposite of what's in the factors. So my tails, or end behavior. If you were to multiply this out, the first term is going to be x cubed. So it's a positive odd, which means my tails look like that. And your y-intercept, what would we get if we set all of the x's equal to 0 and then multiplied everything through? So if you do that, I get 1 times negative 3 times 4, so y equals negative 12. Okay, so let's set this up. Negative 1, negative 2, negative 3, negative 4. So you got a root at negative 4, you've got a root at negative 1, 1, 2, 3, a root at positive 3. The y-intercept down here somewhere at negative 12. And notice your tails. Now what's nice about every single one of these roots has a multiplicity of 1, so they just pass right through. Nothing special. Keeps going right through. And there's your quick sketch of a cubic with multiplicity of 1 for every root. Alright, multiplicity of 2. Again, there's no particular order in terms of finding this information. Roots here, pretty straightforward. X equals 0. That's what I like to call a double root. Usually you're going to see like double and triple roots because it's x squared equals 0. So it occurs twice, and we have x equals positive 2. My tails, or end behavior, If you were to multiply this out, you'd start with an x cubed, so we got positive odd. So my tail is going to do this. And the y-intercept, if you set all your x's equal to 0, you're going to have 0 times negative 2, which is 0. Now again, remember, if x equals 0 is a root, then your y-intercept is always y equals 0. So that should be easy to kind of remember. All right, so I've got 0 for a root here. I've got 2 for a root there. My tails do this. The only way this is going to work is if you remember your multiplicity. All right, x equals 0 is a double root. So remember, it's going to bounce. So it'll come up through, turn around there, and then turn back around and pass through that root at 2. All right, so there's an example with a double. And let's do one more. Actually, let's skip that one. All right, we're going to wrap this up here with even and odd functions, not to be confused with an even degree or an odd degree. So if you notice this function right here, it's got symmetry. If you remember back to your geometry days, this has a particular type of symmetry with respect to the origin. If a function has symmetry with respect to the origin, it's called an odd function. And I know sometimes we get lazy and we just call things odd or even, but really there's a distinction between an odd function and odd degree function. This particular function, as you can see, has symmetry with respect to the y-axis. So if a function has symmetry with respect to the y-axis, it is called an even function. All right, so basically you guys just need to be able to identify odd functions versus even functions. So symmetry with respect to the origin, odd. Symmetry with respect to the y-axis, even. If it doesn't have either one of those, you just say neither. All right, so in this particular one, it's kind of easy to see. Oh yeah, this has symmetry with respect to the origin, so that is odd. Just remember, OO, origin, odd. This particular graph in part B, neither, right? You can't fold it on the y-axis. You can't turn it upside down, rotate it 180, which is the same as a reflection through the origin. This graph here looks a little funky, but if you were to turn this upside down, I know I just did that quickly, but you could see here, oh yeah, it does have symmetry with respect to the origin, so that is odd. Part D, easy to see, reflection in the y-axis, so that's what we would call even. This one here is neither. And this one again, reflection in the y-axis, so that would be even. All right, we don't spend a lot of time on that, but it is something that unfortunately we'll see from time to time on a Regents exam. All right, so finally here, this is a little bit more important, talking about relative extrema. Relative extrema, what we call relative maximum or relative minimum. So relative maximum, the point on the function where the graph changes from increasing to decreasing. So basically here, you want to think of the hilltop. So there's a hilltop. That point right there would be considered a relative maximum. A relative minimum, the point on the function where the graph changes from decreasing to increasing. So there, think of a valley. So here's a valley. That point right there is a relative minimum. So on this random function that is sketched here, there are two relative maximums. Here's a hilltop, here's a hilltop. Those are relative maximums, okay? And there are two valleys, here and here. So those are called a relative minimum. Notice the lowest point on the graph is not necessarily a relative minimum, and same thing with the highest point on the graph. This right here is not a relative maximum because it's not changing from increasing to decreasing. It's not a hilltop. All right, it's just the highest point. That's called something different, an absolute maximum or minimum. All right, so very quickly, let's just do one of these examples here. It says find the coordinates of all relative maximum and relative minimums for each one. So what we're going to do here very quickly is we're going to take our calculators, and I want you guys to put this into y1. So we've got 2x cubed plus 3x squared. So I want you guys doing this as I do it here. Oh, great. Let me do that again. 2x cubed plus 3x squared minus 36x minus 15. Okay, and let's take a look at the picture. So if I want to get the coordinates of relative maximums and minimums, I should know now a cubic goes up, down, back up, so I need to adjust my window. So I'm going to go to my window, y min, let's go negative 50, y max, let's go 50, I'm not going to mess around. Whoa, still need to go more. All right, so y min, let's go negative 75, hopefully this will do it, and positive 75. Perfect, all right. So now a quick sketch. And obviously if I need a relative maximum, I need this point here. If I need a relative minimum, I need that point there. Well, there's no real shortcut way to do this. On your calculator, you have to do second calc, and let's find our maximum first. Usually it's quicker to go left to right. So now it's going to prompt you. It's going to say left bound. So you just have to move your cursor to the left of that maximum, hit enter. Move it to the right, hit enter, and then get it close, hit enter. It's got to say maximum. So right here, this is actually negative 366. To find our relative minimum, what we're going to do is second calc minimum. So we'll go 3. It's going to say left bound, so I got to get it over there a little closer. Anywhere to the left of it, hit enter. Right bound to the right of it, hit enter. And back, hit enter. So this is 2, negative 59. All right, so here we go. There's a rel max at negative 366 and a relative min at 2, comma, negative 59. Okay, even though the graph continues below the lowest or the relative minimum and it continues up beyond the relative maximum, the hilltop and the valley have those coordinates, so those are the rel max and rel min. All right, so this concludes day 3. Once again, please do the associated homework. All the homework keys and note keys are also on Schoology, so feel free to use those to kind of help you through. Thanks.